Welcome all. Now I'm going to discuss about the hardware and software parallelism. In the last class, I have already explained about the conditions of parallelism, which includes Bernstein conditions, data and resource dependencies. Now I move to the next part of the conditions of parallelism, that is hardware and software parallelism. And also I will explain about the role of compiler in the parallelism. We all know the system contains both hardware and software. The hardware parallelism defined by the machine architecture and the hardware multiplicity. And in this session, I will discuss about how the utilization of resources done in the hardware parallelism and what are the characteristics of hardware parallelism. We can also call it as machine parallelism. It's a function of cost and performance trade-off, and it displays resource utilization patterns of simultaneously executable operations. So, the first point is resource utilization. As I said earlier, to achieve the parallelism, we need a joint effort of both hardware and software parallelism. If we have resources and the utilization is proper, so the performance will increase in machine, right? This is called hardware parallelism, and it's characteristic by number of instruction issues per machine cycle. What do you mean by issues? Hope you remember the concept of pipelining. What is it? Fetch, decode, execute, write memory, right? Each and everything in these steps are called issues. Fetch the instructions from the memory, decode or do the arithmetical operations, and execute the instructions and write the result back into the memory. This everything in this instruction is called issues. So in pipelining, each and every clock cycle, all the issues are executing. That's the idea behind this. As I told you, the multiple processor execute multiple instructions in the parallelism manner. Assume that we have three issues: arithmetic and logic, memory fetching, and branching. That is, these three issues per clock cycle, processor can do the three instructions simultaneously in one clock cycle. So we can say that it is a three issue processor. So what is K issue processor? That processor can do K instructions simultaneously in one clock cycle. That is called K issue processor. A multiprocessor system with a K-issue processor can handle a maximum limit of n K parallel instructions. That means n parallel threads at thread level parallelism. That is called TLP, thread level parallelism. And look at this last point, representative systems. There are two systems. These are the examples for hardware parallelism implemented processors. First one is Intel i960CA. This is the three-issue processor, that is arithmetic, memory access, and branching. These are the three issues in Intel i960CA. And next one is RISC System 6000. It is made by IBM, and this is the four-issue processor. The floating point issue is added with arithmetic, memory access, and branching issues. These are the examples for hardware parallelism. And next one is software parallelism. It's defined by the control and data dependence of programs. We have already discussed about the data dependence, and it is relieved in program profiling or program dependency graph. It's also known as data flow graph. For representing software parallelism, we can use the flow graphs. That means it displays the patterns of simultaneously executable operations. And the software parallelism depends on algorithm of the program, parallel task grain size, programming style, and also the compiler optimization. And the software parallelism can be of two types, control parallelism and data parallelism. Next, consider this example. We can analyze the mismatch between software parallelism and hardware parallelism using this example. Consider two instructions, A and B. A means L1 star L2 plus L3 star L4. This is the first instruction. It is denoted as A. And B means L2 star L1 star L2 minus L3 star L4. This is the instruction B. So we can say that there are 8 instructions. How? First of all, in cycle 1 there are 4 load instructions, L1, L2, L3 and L4. Load these variables. And next 4 arithmetic operations. That means in the second cycle there is 2 multiplication stars, star 1 and star 2. And in cycle 3 there are 2 more arithmetic operations, plus and minus. So we can say that there are 8 instructions like 4 load operations and 4 arithmetic operations, right? To be executed in 3 consecutive machine cycles. As this figure, in cycle 1 the machine load 4 variables L1, L2, L3, L4, and in cycle 2 the variables are multiplying each other, L1 star L2 and L3 star L4, and in cycle 3 it's added with L1 star L2 plus L3 star L4, and also L1 star L2 minus L3 star L4. These cycles can execute parallel. So followed by 2 multiply operations in second cycle and 2 add or subtract operations in third cycle, as I said earlier. Therefore, the parallelism varies from 4 to 2 in 3 cycles. So we have only 3 cycles here for using the software parallelism. So what is the average software parallelism? So it is equal to, there are 8 instructions, right? So 8 divided by, there is only 3 cycles. So 3. 8 divided by 3, we will get 2.67 instructions per cycle. So this is the average software parallelism in this example. But this is example for hardware parallelism for the same instruction. For hardware parallelism, we want 7 cycles for executing this A and B instructions. First of all, load the first variable L1, and in cycle 2 load second one, and in third cycle load third variable, and with that we will multiply these 2 variables in the same cycle, cycle 3. And the next cycle load fourth variable, and fifth cycle we multiply these 2, and in the sixth cycle add these, after multiplication the result will add with each other, and in last cycle, cycle 7, the subtraction is possible. So for hardware parallelism we need 7 cycles. So what is the average hardware parallelism? So there is 8 instructions and we need 7 cycles for executing this. So 8 divided by 7, 1.14 instructions executed per cycle. It demonstrates the mismatch between the software parallelism and hardware parallelism. Hope you understand about the mismatch of hardware and software parallelism through this example. And as I said earlier, there are two types in software parallelism: control parallelism and data parallelism. What is control parallelism? It allows two or more operations to be performed simultaneously. While in data parallelism, at most same operation is performed over, but many data elements by many processors simultaneously. That is the main difference between the control parallelism and data parallelism. And the next topic is the role of compiler. What is the task of compiler? Compiler is a program that translates the high-level language into machine-readable form. So the hardware processors can be better designed to exploit the parallelism by an optimizer compiler. In the previous classes, we discussed about the optimizing compiler and its tasks or duties. And that is the compiler techniques are used to exploit the hardware features to improve the performance. Such processors use large register file and sustained instruction pipelining to execute nearly one instruction per cycle. This is the advantage of compilers, that is optimizing compilers. And the large register file supports fast access to temporary values generated by the optimizing compiler. And the registers are exploited by code optimizer and the global register allocation in such compilers. And this is the end of the conditions of parallelism and also the module 1. Hope you understand about these conditions of parallelism. Thank you.